Nice to meet you. I'm Khatar Choktai and you're watching my YouTube channel, School of Advanced Chemistry. I'm going to explain stability constant. This topic belongs to inorganic chemistry for A2 chemistry students. Let's talk about it. Stability constant that is applicable in ligand exchange reaction. Basically, ligand exchange reactions are equilibrium reaction. I mean, when the ligand exchange is going to happen, then at that time, when one ligand is going to replace another ligand, at that time, the overall reaction is reversible reaction. And there is happening of a dynamic equilibrium, or you can say there is a stage of dynamic equilibrium is going to establish. So basically, when this stage has been established, at this stage, we can calculate a constant like Kc is called K stability. For example, we are having a complex that is copper hexa aqua copper complex H2O 6 copper 2 positive ion aqueous. This is a pale blue complex, and if I am going to add aqueous ammonia into this complex, and especially if I'm going to add excess aqueous ammonia into this complex, then in fact this reaction is a reversible reaction. First it proceeds in forward direction, then after some time it will start proceeding towards the backward direction. So what is happening, what will form finally, we see that there is a deep blue solution whenever we are going to add excess ammonia into the sample of aqueous copper, that is basically the complex ion, hexa aqua copper complex ion, and finally we are going to observe the deep blue solution. The deep blue solution is because of this complex. CuNH3 4 tetraamino complex is basically this one, H2O2, and it's having 2 positive charge again. But the color of this complex is deep blue. Initially, its color was pale blue. This overall reaction is said to be or known as a ligand exchange reaction, and here is its overall equation. Its balanced equation or overall equation for this reaction. First, initially is there the forward reaction, then after some time there is the reverse reaction. A stage will come when the rate of forward reaction is equal to rate of reverse reaction. At this stage, the reaction is complete. So we are going to see the color has been changed and there is a deep blue color. So here, as you know, we can find equilibrium constant for all type of reactions where there is dynamic equilibrium. And that is called, that may be in form of Kc, equilibrium constant in terms of concentration, that may be in form of Kp, equilibrium constant in terms of partial pressure, that may be in form of Ksp, that may be in form of Kpc and so on. So here we can find, we can calculate, we can write the expression of Kc of this reaction that is called basically it's Kstab, Kstability I mean. So in this way we call it Kstability. But in fact these all ammonia are not going to substitute water molecule at once. This is a continuous process. NH3 is introduced, or NH3 molecule is going to replace H2O molecule turn by turn. How? Let's see over here. For example, in this case, initially CuH2O6 2 positive plus NH3 1 mole of NH3, and here is the formation of N copper Cu NH3 1 and H2O5 bracket close, it's having plus 2 plus 1 mole of H2O over here. This is the first step of this reaction. And let's suppose we are going to say it K1. Kstability 1. Step 1 Kstability. Step 1 Kc you can say is equal to K1. What is the next step? The next step is Cu, that is having one ammonia over here and 5 H2O molecules with two positive charge. Another ammonia is going to exchange in replace the water molecule. NH3 goes to, there is Cu NH3 twice. Now, initially it was one over here. Now it's twice, and H2O is now 4 rather than 5. And it is having again two positive ion plus H2O. On each step, every time there is the replacement of or the formation of, you can say, water molecule. What is the next step? What it could be? In next step, Cu NH3 twice, I mean starting from here, H2O 4, this complex is going to further react with one more mole of NH3. It's again a reversible reaction, and this is said to be formation of the next complex, that is NH3 thrice, H2O thrice as well, and two positive charge, plus there is formation of H2O molecule. The second, for the second equation, the equilibrium constant is called K2. The stability constant, or Kc, for the second reaction is K2. The K stability, or Kc, for the third reaction is, let's suppose, known as K3. Now come to the last step. In last step, there is the final introduction of the fourth ammonia ligand. Cu NH3 thrice, H2O also thrice, two positive ion, plus the last, fourth NH3, going to make a new complex, Cu NH3 4, and H2O going to have two positive charge, and H2O. And its K stability, its Kc, that is a K stability basically, is K4. So I have replaced all 4 molecule by 4 NH3. And remember one thing, with the copper complex, you can only substitute 4 NH3. Why is this so? Why we cannot appreciably replace, or we cannot introduce more than 4 ammonia ligand in these sort of complexes? The basic answer is K stability. So what K stability mean? Basically, the K stability is that is showing the stability of, or the value of Kc. K stability is the equilibrium constant, as I told you. It's an equilibrium constant for the reaction in which a complex is being formed from its aqueous sign. So once again, I'm going to repeat it once again. Stability constant is an equilibrium constant when a complex ion, this is a specific word, when the complex ion is being formed from its aqueous sign. A new complex ion is being formed starting from its aqueous ion. This is called stability constant, or stability, Kstab in short, or in abbreviation word you can say. So basically, K stability tells us how the newly born complex is stable. That's why it's called K stability. How the newly born, newly formed complex is more stable than the previous one. For example, K1. K1 mean here are two complexes, this one and this one. What will be the expression of K1? In K1, we will write K1. Here, I am going to write the product over here, And product mean there is the complex and water molecule. This is the complex and water molecule. These are called the product. And these two species are known as the reactant. So as we will write the Kc, concentration of the product divided by the concentration of the reactant. But in this case, we are not going to count water molecule. We are not going to count the concentration of water because the water is in excess. This complex is already an aqueous complex and there is no need to count water. I mean, the value of the water will be constant. It will be equal to 1. So what is on the right hand side? I mean, what are the remaining products? That is this one. Cu NH3 H2O5 2 positive ion. That's all. So this is the basically a complex formed over here, and you can say this is the concentration of this complex ion. You can mark as well, this is the concentration of this complex ion. Now divided by what was the initial complex? Cu H2O6 2 positive. The concentration of this complex multiplied by the concentration of NH3. This is the true expression of Kstability of one step. And let's suppose from the data booklet we can see that its answer is 1.58 into 10 raised to power 4. It's a huge value. It's the biggest value, you can say, in this scenario. So basically, it means that this complex that is being formed over here from the aqueous one, so mono amino copper complex is more stable, is very stable as compared to this one complex that is hexa aqua copper complex. So this is what meant by the Kstability. Basically, the Kstability is going to give you the comparison of the stability of the two complexes. One that is newly born and other one that was the parent complex. So in this case, you can easily, rapidly, abruptly, you can say, you can introduce one ammonia ligand in this complex. So this reaction, you can say, is almost happening in forward direction. Because the value, if the value of Kc is very high, then you can say the reaction is all the time is going toward the forward direction. So generally, the reverse reaction is very less, or you can say it is up to the negligible extent. But yes, it is over here because it's a reversible reaction. But as far as the stability constant is concerned, this complex will form immediately. Now come towards K2. The K2, similarly, we can write the expression of K2 as well. The expression of K2 is, I'm going to write it over here. So let's see over here. For K2, the K2, the basic complex is Cu NH3 twice H2O4 2 positive ion concentration and divided by Cu NH31 H2O5 into NH3 concentration, and it is also having 2 positive charges. So this is the true expression of Kstability, Kstab for second step, and its answer or its value is basically 3.2 into 10 raised to power 3. So you can see that you can compare these two answers. It means that the second constant K2 is less, or it is less worthy, it is smaller than that of the first one. It means this complex is less stable. If I'm going to compare these two complexes, so this second complex that is having 2 ammonia ligand is less stable as compared to the first one, as compared to this one that is having 1 ammonia ligand. And same is the case in this case again As I told you, this one and same thing. The newly born complex is more stable. So same is the case with the K3 stability constant, that is less than that of K2, and K4 is less than that of K3. If I'm going to write the K5, if I'm going to introduce the fifth ammonia ligand, the value is very much low. Almost that is equal to, you can say 0.32 is the its K stability for the introduction of fifth ammonia over here. So that's why fifth ammonia, the next ammonia we cannot introduce into this complex. This is the final complex. As far as the copper complex with the ammonia is concerned, this is the lowest stable, you can say, but the stable complex. Beyond this level, there will be least stability, or the less stability of the complex will be there. So we can easily introduce only 4 ammonia ligand. Similarly, we can write the overall case stability expression for this one, for this complex, for example. So same is the procedure. Case stability is equal to Cu NH3. I'm going to write it over here. NH3 4 into H2O twice, and 2 positive charge. There is no water, as I told you, and in denominator there is a complex of copper hexaaqua complex, and it is 2 positive charge. This is the bracket of concentration, and multiply by the concentration of initial concentration of the concentration at equilibrium of NH3. So again, the answer of this stability is going to give us the overall picture of this change. The overall case stability of all 4 steps, that is having this one expression. You can also find the overall stability for first 2 steps. You can also calculate, you can also write the expression for the overall stability constant for first 3 steps, and similarly overall stability constant for all first 4 steps, and so on. So that is the basic concept of K stability, or stability constant, at the stage of dynamic equilibrium whenever you are going to perform ligand exchange reaction. That's all about today. Thank you very much. Have a nice day. Please subscribe my channel, hit the bell icon, and share it with your friends. Thank you.